The hidden hero of heavy trucks, understanding the bell crank. Welcome everyone to this explainer. Today we're looking at something you probably pass on the highway every single day without ever giving it a second thought. I'm talking about those massive heavy-duty transport trucks, the ones hauling just unimaginable loads across thousands of miles. We all know they're built tough, but there is this absolutely fascinating mechanical battle happening right underneath that massive chassis, the second the road stops being perfectly flat. Specifically, we're going to unpack exactly how multi-axle trucks manage to survive uneven terrain, deep potholes, and severe bumps without completely destroying their own wheels. It's a brilliant piece of hidden engineering, and to truly understand it, we need to look right under the truck bed. Okay, let's dive into this because this is where the physical stakes get incredibly high. Just imagine a truck carrying tens of thousands of pounds of cargo cruising down a road. Now visualize what happens the split second it encounters a simple speed breaker. We've all driven over them in our cars, maybe felt a slight jolt, right? But for a truck carrying immense weight, actually scratch that. It's not just an annoyance. It is a sudden, violent physical obstacle. The forces at play here are astronomical. So what actually happens to the physical structure of the truck in that exact moment? Let's break down the mechanics. Section 1. The multi-axle problem. Adding more wheels. To carry more weight, engineers follow a pretty simple rule. You just add more axles and more wheels to the rear of the truck. This distributes the heavy payload across a much larger surface area on the road. And hey, it makes perfect logical sense on paper. However, introducing multiple axles right next to each other creates a massive mechanical vulnerability when the road is no longer perfectly flat. The very solution used to carry those heavy loads suddenly introduces a completely new conflict. Think about the stark contrast between these two setups. On one hand, a single rear axle handles bumps beautifully. When a truck with just one rear axle hits a speed breaker, the entire rear suspension simply travels up and then back down, crossing the bump easily. The load shifts briefly, sure, but it's totally manageable. But on the other hand, the moment you add a second axle right behind the first one, the physics change entirely. Suddenly, these two rigid points on the truck's frame are dealing with an uneven surface at different times. They literally begin to fight each other for space, forcing the entirety of the truck's massive cargo load onto a very isolated point. And this brilliantly illustrates the exact mechanical conflict happening beneath the vehicle. The more axles you add to the rear of a heavy truck, they actually become enemies of each other. I just love that phrasing. It's a fantastic way to personify what's going on. Instead of working together to share that massive burden of the cargo, an uneven surface forces these axles to brutally compete. Because the truck body itself is rigid, when the front axle is pushed upward by an obstacle, the geometry of the entire rear section gets completely distorted. Let's walk through exactly what this speed breaker disaster looks like in motion. First, the front tire of that multi-axle setup hits the bump and is violently forced upward. Instantly, because the wheels are locked in their positions relative to the frame, that single front tire takes the entire weight of the truck's rear. Meanwhile, the rear tire is lifted entirely off the ground. It's just left hanging uselessly in the air, doing absolutely nothing to support the cargo. Now, if that front tire miraculously survives that immense pressure without bursting under the strain, the truck rolls forward, the front tire drops, and boom, the rear tire hits the breaker. This means the rear tire now violently takes that full, brutal load. It's just a catastrophic sequence of impacts. Obviously, heavy trucks aren't constantly blowing out their tires every time they go over a speed bump. So how is this catastrophic mechanical problem actually solved? Section 2. Enter the bell crank, the unsung hero. This brings us to a specific piece of hardware designed to intervene and save the truck from literally tearing itself apart. So the absolutely crucial point here is understanding what this mechanism actually is. It's called a bell crank. At its core, a bell crank is simply a central rotating pivot. It's an incredibly clever lever system. If an upward force is applied to one point of the bell crank, it rotates around its center and instantly redirects that energy, transferring it as a downward force to another point. It takes the violent, destructive energy of a bump and completely redirects it exactly where it needs to go. Let's visualize how this whole setup lives underneath the truck. You have your leaf suspension, those incredibly thick curved layers of steel, which is securely fixed right onto the axle itself. Now, one side of that leaf suspension connects directly and rigidly to the heavy body of the truck. But the other side? That side connects directly to our hero, the bell crank. So instead of the suspension being completely locked in place at both ends, the bell crank acts as a dynamic, moving joint between the heavy frame and the axles. Section 3. How mechanics work. Split-second physics. Now that we know where the bell crank lives, we need to look at how it operates when the rubber actually meets the road, or, well, in this case, when the rubber meets the speed breaker. We're going to break down the split-second physics that occur to save these multi-axle systems from a total catastrophic failure. Let's move to and see how this builds. Imagine this happening in extreme slow motion. Step 1. The front wheel pair of our multi-axle setup hits the speed breaker and is violently forced to rise. Step 2. As that wheel is pushed up, the leaf spring pushes on the bell crank, causing it to instantly rotate from its center point. Step 3. We have a tie rod connecting the front suspension to a secondary bell crank in the back, and the force transfers instantly across this rod. Step 4. Because of how the bell crank just rotated, that upward energy from the front wheel is perfectly inverted, and a massive downward force is actively pushed right onto the rear wheel pair. It is a beautifully engineered balancing act. Honestly, think of it exactly like a giant seesaw. By tying the two independent axles together through this rotating pivot, they can no longer fight each other. When the front axle goes up to clear an obstacle, the bell crank physically pushes the rear axle down so that its tires stay firmly planted on the flat ground, sharing the load. And conversely, as the truck moves forward and the rear axle goes up over the bump, the bell crank rotates the other way, pushing the front axle down. They're constantly reacting to one another in real time. It's a continuous mechanical dance. Section 4. Surviving the bump. Neutralizing danger. Through this highly dynamic mechanical linkage, what was once a disastrous physics problem, rigid axles fighting for space and destroying tires, is completely neutralized. The engineering has actively triumphed over the destructive forces of the road. Now, what's really interesting here is the final result of all that mechanical action. The load transfer is completely fluid. In that critical condition where one wheel is elevated, both axles use the bell cranks to instantly transfer and balance their load. Instead of one single tire taking 100% of a massive multi-ton cargo and immediately bursting under the pressure, the weight is continuously shared across all the wheels on the ground. This simple rotating pivot prevents total mechanical failure every single time the truck hits a bump. It really makes you appreciate the invisible ingenuity happening right beneath our feet, doesn't it? A massive, potentially disastrous problem solved by a relatively simple, elegant rotating lever. And it leaves you wondering, as we drive down the highway surrounded by these massive machines, what other hidden mechanical heroes are silently operating in the vehicles all around us, keeping the whole world moving safely? Keep that curiosity alive, and thanks so much for joining me for this explainer.